Helminth parasites, also known as worm infections, can cause severe disease and are amongst the most important production-limiting diseases of livestock. Reliance on chemical anthelmintics, or wormers, to control these infections has resulted in a selection of drug-resistant helminth populations. Sustainable, integrated parasite control programs in ruminant livestock will require a higher uptake of anthelmintic efficacy and resistance tests. Different approaches have been proposed and used for the assessment of anthelmintic efficacy and hence the diagnosis of anthelmintic resistance in ruminants, including tests conducted in animals. The fecal egg count reduction test is considered the mainstay for the assessment of the anthelmintic drug efficacy and hence the anthelmintic resistance and can provide a measure of the performance of a number of different anthelmintics at the same time. Using the fecal egg count reduction test, the efficacy of an anthelmintic is assessed by quantifying the reduction of a helminth egg output in a group of animals tested before and after treatment. The first step to assess the possible presence of anthelmintic resistance on a farm is to understand its management and know the anthelmintic regime regularly used. In order to evaluate anthelmintic efficacy of a drug on a farm, sampling must be conducted correctly and enough animals selected to provide representative results. Collect individual rectal fecal samples, a minimum of 20 grams for cattle and 2 to 5 grams for sheep and goats, from a minimum of a number of 10 animals per group on selected farms. Higher numbers, where available, will allow a more representative result. Cattle in their first grazing season are preferable. For sheep and goats, animals of all ages may be used. To identify animals with high egg counts, 15 or more animals can be selected pre-treatment, with post-treatment sampling focused on the 10 animals with the highest egg counts. Samples should ideally reach the lab on the day of sampling and be cooled to below 10 degrees Celsius during transport. If cooling is not possible, eggs can be transported at ambient temperature in a sealed bag, squeezing as much air out as possible. Whichever route of administration for an anthelmintic drug is used, it is important to read the manufacturer's instructions carefully. The first step to perform a good anthelmintic treatment is to choose the most appropriate class of anthelmintics based on prior parasitological diagnosis and identify the correct dosage. The dose should be applied according to individual live weight or to the weight of the heaviest animal using scales. Weighing bands or a smartphone app can be used for cattle. Temporary feed restriction prior to anthelmintic treatment has been shown to increase the absorption and bioavailability of anthelmintics. Reduced feed intake reduces the digestive flow rates and decreases the rate of passage of the anthelmintic down the gastrointestinal tract. Before administering an oral anthelmintic suspension, shake the container to administer a homogeneous suspension to all animals. It is very important before performing the treatment to calibrate the drug dispenser and administer the drug correctly. After the treatment, make sure that the drug has been taken by the animal. The same animals must be sampled pre- and post-treatment specifically on day 0 and between 7 to 21 days after treatment, depending on the anthelmintic group tested. On each individual sample, a fecal egg count is performed to obtain data on the number of worm eggs per gram of faeces. This procedure uses a quantitative copro-microscopic method, for example, McMaster. When low numbers of eggs are expected, sensitive methods such as mini flow tech are recommended. To ensure reliable conclusions on drug efficacy, a minimum number of 200 eggs per treatment group need to be counted prior to treatment. This is the total number of eggs actually counted across the 10 animals sampled, not the number of eggs per gram. Therefore, if this number was not obtained following the analysis of all samples, the practical solution is to examine a second aliquot of each of the same samples, thus leading to an analytic sensitivity of 2.5 eggs per gram, if, for example, a mini flow tech is being used. Subsequently, the same analytic sensitivity must be employed also when examining the post-treatment samples of the same animals. Eggs at this stage are expected to be fewer in number, and the minimum target of 200 eggs counted does not apply. Although results are less reliable and no confidence intervals can be added to measured percent fecal egg count reduction, the recommended method to calculate the fecal egg count reduction with confidence intervals is the R package, egg counts. The drug efficacy is classified as reduced, doubtful, and normal, depending on the fecal egg count reduction percentage and the value of the lower limit of the 95% confidence interval. It is useful to know which species are surviving treatment. These can be identified either using morphological examination of mature third-stage larvae from coprocultures or using molecular techniques with DNA extracted from eggs, hatched larvae, or mature larvae following coproculture. Separate pooled samples should be prepared using fecal samples which were not cooled, since cooling may affect the hatching or larval development. A vision promoted within COMBAR has been that a rapid fecal egg count reduction test based on an easy-to-perform, low-cost and reliable tool may increase the user-friendliness and uptake of fecal egg count reduction test by veterinarians, advisors and farmers. The impetus by the scientific community, as well as by stakeholders and end users, and the quickening pace of technological innovations are promoting a renaissance of interest in the diagnosis of anthelmintic resistance. This can provide vital and timely information to support parasite management decisions on farms and prolong the useful life of anthelmintics. Don't wait, just do it.